Hello everyone. In the last video we looked at temperature and rate of reaction, and we explained how temperature affects the rate of reaction using collision theory. In this video we're going to look at another factor that affects the rate of reaction, which is concentration. And in fact this is the required practical for this unit. So first of all you need to be able to make a prediction using collision theory, and then you need to be able to test that prediction by designing an experiment that either measures the volume of gas, or if a solid is made and the solution goes cloudy, you need to use the disappearing cross method. So we're going to take a look at both methods in case you get asked about one of them on your exam. Before we look at the practical, investigating how concentration affects the rate of reaction, first we're going to see what we mean when we talk about concentration. So in everyday terms, if we were making some orange squash with some orange juice and water, dilute or less concentrated means we would use less of the chemical, less of the orange in other words, and more water. If we were making a concentrated drink of orange squash, we would use more of the orange and not quite so much water, so there's more of the chemical in there. What does that mean in terms of the particles though? So if we have a look at the particles of a dilute solution and a concentrated solution, we can see in dilute reactants or low concentration, there's less particles of the chemical in the same volume of water. You can see the reactant particles are much less crowded. In a more concentrated reactant, or if we say that we've got more particles of the chemical in the same volume of water. Or another way of saying that is the reactant particles are more crowded. We're going to use collision theory to make a prediction. So the question you could be asked on an exam is use collision theory to predict what would happen to the rate of reaction if you increase the concentration of the reactant. So pause the video here, write down an answer, and then resume the video to see if you're correct. So the answer would be, if the concentration is increased, there will be more particles in the same volume, or in other words, the reactant particles are more crowded. So that means there would be more frequent collisions and therefore a higher rate of reaction. This is the first method of investigating how concentration affects the rate of reaction. So I've got a gas syringe to collect any gas that's given off over a certain time period. I've got different concentrations of acid. So in an exam, you would describe how to do your experiment with your first concentration of acid. So you might say, for example, measure out using a measuring cylinder 50 centimetres cubed of the acid and place it into a flask. So be specific with your amounts. So anywhere up to 100 centimetres cubed would be appropriate, somewhere on the scale of the measuring cylinder. And then we will add a known mass of magnesium. In this case I've got 0.5 grams of magnesium already weighed out, and I'm going to measure the volume of gas for 20 seconds each time. So I'll put the magnesium into the acid and then quickly replace the bung. Start the stopwatch so I can see how much gas is produced in 20 seconds by reading it off the gas syringe. And then once I've done that, I would describe how to do it again using the different concentrations. So we can see the gas syringe is being pushed out because all the tiny gas bubbles are being collected by the delivery tube, and then that's being collected by the gas syringe. So in this case it's measured 10 centimetres cubed of gas in 20 seconds. I'd then discard that and I'd repeat the experiment again using another 0.5 grams of magnesium. I would use another 50 centimetres cubed of acid, but this time I would change the concentration. So if I started with 0.25 moles per dm cubed concentration of acid, I would then increase it to 0.5 moles per dm cubed, ideally with 5 different concentrations. So when you're writing about these, be specific with your amounts, say what equipment you're using along the way, like measuring the volume of gas with a gas syringe, measuring the volume of acid with a measuring cylinder, similarly using a balance to measure the mass of magnesium. We're now going to look at a second way in case a solid is produced in the reaction, and in that case we're going to use the disappearing cross method. The second method of investigating how concentration affects the rate of reaction involves the disappearing cross method. So what we're going to use is 50 centimeters cubed of sodium thiosulfate. So once again, it's important that you say the volume of any reactants that we're going to use. And we're going to put that into a conical flask, and the conical flask is stuck on top of a piece of paper with an X on it. And then we're going to use the same volume of hydrochloric acid. And as soon as those reactants are together, give it a little swirl and start the stopwatch. So this is one of those situations where a solid is produced by the reaction. So in the symbol equation, one of the reactants will have an S next to it to show the state symbol for a solid. So in this case, the sulfur would have an S next to it. So that would give you a clue that this is the method you need to use, the disappearing cross method. So we've put the cross underneath the flask, so we're measuring the time it takes to go so cloudy that we can't see the cross through the reactant. So I can't see the cross anymore, I'll stop the stopwatch, and that will be the time taken to go cloudy with my first concentration of acid. I would then repeat that with different concentrations of acid. So in this case, the independent variable is the concentration of acid. That's what we're changing each time. The dependent variable is the time taken for the solution to go cloudy. And the control variables, we've got the same volume of sodium thiosulfate, also the same concentration of sodium thiosulfate, that's not changing. And another control variable is the same volume of hydrochloric acid. And once again, when describing the method, it's important you state the quantities. So anywhere up to 100 centimeters cubed would be appropriate. Say what equipment you're using to measure out as well. So measuring 50 centimeters cubed of the first reactant with a measuring cylinder, for example.